Hello and welcome to Cryogenic Chambers, where we take moments in time and freeze them. We are joined by professors Nicole Ramos and
Liza St. Augustine
of Professor Rodin's Applied Physics Class 141, Fall 2014 semester.
Today we will freeze Evel Knievel's King Island's jump and analyze this daredevil stunt with physics. Please turn your attention to the screen. So we know that the Greyhound buses are lined up to a combined length of 133 meters with a height of 3.4 meters and are hypothetically inclined at 75 degrees above the horizontal. Assuming the cyclist is traveling at a constant speed, acceleration in the x direction will be zero, since the force of gravity does not act upon this axis.
And acceleration in the y direction will be negative 9.8 meters per second squared, which is the universally accepted constant of gravity. What is the minimum speed required for the stunt driver to clear the 14 Greyhound buses? Recall in our Chapter 2 lesson the list of kinematic equations for constant acceleration.
However, for this problem, we have direction in both the x and y axis, meaning we'll be using two-dimensional kinematic equations explained in Chapter 3. Now we'll organize our given information into a table of values. Since Evel started at rest, the initial position of x and the initial position of y will be 0. The final position of x will be 133 meters to clear the buses. And in the y direction, it will be negative 3.4 meters to land on the opposite declining ramp.
Acceleration in the x direction is 0, and in the y direction is negative 9.8 due to gravity.
Time and velocity are unknown. As you can see, there are still some components missing from our data that are impervious to solve for the minimum speed. To help us solve for those components, we'll be using the 75-degree angle. Notice the 75-degree angle is a right triangle. This allows us to use the trigonometric functions from trigonometry. From this right triangle, we can find the initial velocity and final velocity in the x direction, and initial velocity in the y direction. In a right triangle, there are three sides. For this example, the hypotenuse is velocity, side opposite is y, and side adjacent is x. Sine theta equals opposite over hypotenuse, which gives us sine 75 degrees equals y over velocity. Or in this case, it gives us the initial velocity in the y direction equals v sine 75 degrees. And cosine theta equals adjacent over hypotenuse, which turns into cosine 75 degrees equals x over velocity. That gives us initial and final velocity in the x direction equals v cosine 75 degrees. And if you're wondering why they are the same, it is because they are going in the same direction.
Since velocity is undetermined, we will use v sine 75 degrees and v cosine 75 degrees to substitute into the kinematics equations. We will use kinematics equation number 2 in both the x and y direction to create our modified formulas that will help us determine time. So using our given values, we will plug into the equation and simplify. So we know that x is 133 meters and the initial position of x is 0. Because velocity is undetermined, we will use v cosine 75 degrees times time plus 1/2 times acceleration times time squared, which will be 0 since acceleration in the x direction is 0, which then gives us our modified equation 133 equals v cosine 75 degrees times time in the x direction.
So now our y value will be negative 3.4 because of the declining ramp, and the initial position of y will be 0. Because velocity again is undetermined, we will use v sine 75 degrees times time plus 1/2 times negative 9.8 acceleration due to gravity times time squared. 1/2 of negative 9.8 is negative 4.9, which gives us our second modified equation. Negative 3.4 equals v sine 75 degrees times minus 4.9 times time squared for velocity in the y direction.
Using these formulas for velocity, we will now solve for time. First, we will revise the first equation in terms of velocity, which will give us 133 divided by v cosine 75 degrees times time. We will substitute this value for v into our second equation. So we have negative 3.4 equals 133 divided by cosine 75 degrees times time multiplied by sine 75 degrees times time minus 4.9 times time squared. Knowing trigonometric identities, sine over cosine equals tangent, and the coefficient for time will cancel out. So now we have negative 3.4 equals 133 tangent 75 degrees minus 4.9 times time squared. 133 times tangent 75 degrees gives us 496.36, which we will subtract from negative 3.4. To further isolate the coefficient of time squared, we will divide both sides by negative 4.9, leaving us with 101.9 equals time squared. Taking the square root of both sides, that gives us our final value of time, which is 10.1 seconds.
So now to solve for velocity. We will substitute time in our modified equation for velocity in the x direction, which gives us 133 meters equals v cosine 75 degrees times 10.1 seconds. To isolate velocity, we will divide each side by cosine 75 degrees times 10.1. This gives us velocity equals 133 divided by 2.61. So our final answer for velocity in the x direction is 51.0 meters per second. That means that our stuntman would have to be traveling a minimum of 51.0 meters per second to safely clear the jump. In conclusion, for any daredevil stuntman, athlete, engineer, or myth-buster enthusiast, the application of physics can make the difference between success and epic failure. In this case, our stuntman was able to safely clear 14 Greyhound buses thanks to the science of kinematics and projectile motion. Although kinematics is difficult to understand at first, with practice in real-life situations, it can be useful to a variety of people and professions.